All right. So what we're going to do into this class is we're going to talk about the basic application or of superposition of waves. This is the second worksheet for our waves chapter. That's the name that I preferably gave. The word superposition is nearly identical to the word interference, but they are not essentially the same. If I give you a bit of an idea, the idea of superposition essentially mean that the merging of two waves which are somewhat similar to each other. I'm using the word somewhat because in many cases the two waves might not be exactly similar to each other. For example, if we are trying to produce combined wave behavior with two sources which are identical, we're going to get one type of behavior. So what I actually discussed in our last class to take that whole thing into perspective, that if we have two coherent sources, let's say these are the two coherent sources, and this is the approximate midline, as well draw this with a straight line. This is the approximate midline. And if we have a screen right over here, let's say that screen a bit darker. Let's say if we have a screen over here. In that case, well, these two coherent sources cannot be created from two different light sources. I'm going to talk about why can we not create coherent sources from two different light sources. Let me pull this up piece by piece. Any light source that we regularly use on a regular life basis, they are usually a vivid source. Vivid source means there are a lot of light producing units. For example, if you think for a filament lamp has a coil of filament all of which glows. So typically the way, not typically, I mean, essentially the way a filament lamp produces its light is that we send electricity through it, which because of the resistance of the filament, it's a very long thin wire coiled in a very small space, it heats up. And whenever it heats up, the electrons are excited to a higher shell and from the heat energy. And whenever the electrons come back to their original shell, they give up infrared radiation, they also give up visible light. So they gave both of them out. So we have the heat generation and heat leading to light energy for the case of filament lamps. If you think for other sources, like for example, fluorescent lamps that we have, the tube lights, regular tube lights, we usually have length of gaseous mercury. Typically we use mercury for white fluorescent lamps. So they are a vivid source. The reason I'm emphasizing this term vivid to give you a sense that light is not essentially made from a point source. So there are multiple different atoms or multiple different electrons movement which is responsible to produce light from any given light source. We can never absolutely control all of their motion at the same time unless we are talking about laser. Laser is a different thing. Laser need to parallel put it. So we're going to talk about laser after a slight while. But for regular light sources, we cannot control all the jumping back and forth of all the electrons and all the light production from all the individual atoms very precisely. We cannot do that. I mean, it's impossible because at atomic level, we don't have that control. So if we have two different light sources, for example, let's say if we place one light source over here and an identical light source over here, manufactured in the same factory, manufactured in the same environment, even so, we cannot essentially control exactly at what point the light rays are created and at what instant the light rays are created over here. So it is evidently logical that if you even consider for the central maxima, at any instant, all the light rays that will be coming in from this source and all the light rays which will be coming in from this source, they will never be completely in phase, because it is possible that it produces a light ray over here, it produces another light ray over here, let's say quarter of a time period after the next light is produced, let's say 0.1 times time period after of a quarter of a time period. So you cannot essentially we cannot essentially make them synchronized in terms of their phase. That's not going to work out. So what happens that even if we have multiple light sources in our vivid light sources, we are never going to be able to see a pattern over here. One of the things that I need to understand that in our houses as well, we might have multiple light sources in different parts of the room. A single room can have two light sources, three light sources. But on the wall, if you have any color of wall, we never see an interference pattern. The reason is that, so if you wonder that because we do not see an interference pattern, does this mean that continuously that there is no superposition, or there is no interference, or there is no merging of the light waves to give us constructive or destructive? Is it not happening? The answer is it is happening, but it is changing so fast that our visual equipment, the eyes, we cannot capture that information. For example, in the same location, let's say at one instant you are having constructive, in the very next instant you're having destructive, and in the next in the very next instant you're having halfway constructive or destructive. So the intensity of all of these points on this wall, if you have two individual sources, they are changing randomly over time, which will make the entire wall to give us an uniform illumination, but we cannot get perfect dark in some places or perfect black, perfect white in any places. So point to be noted, whenever we have two wave sources sending waves to one location of a medium, interference will happen, superposition will happen, alternatively constructive and destructive interferences can happen. But whether they will be visible or not is highly dependent on if those two sources are coherent or not. If these two sources are coherent, they'll be sending waves in a known pattern. That will give us an obtainable visible pattern onto this screen so that we can have bright and dark locations. Other than having that pattern, other than having these two sources being coherent, superposition will happen, but that effect will not be observable. So that's one of the key part that we need to understand. That is the importance why we have to actually have a, let's say, single light source over here. Then we usually have a one cardboard piece. We make one slit at the center of this cardboard piece, which was as our single source, and that gives us the light over here. So light rays reaches over onto these two sources, and these two sources behaves pretty much exactly same because they are coming in from one single point light source, and there is not a lot of individual sources which are producing these waves. So their behavior are perfectly identical because they are created from one single dot of hole, not an individual illuminator source. I mean, why am I emphasizing this? I mean, you might wonder that why don't we just keep a light source over here and do this over here? Well, then the problem still remains that this source and these two individual holes, if we don't have this screen, they are going to receive different phase of the light waves at different time instances. So there wouldn't be any pattern, or there wouldn't be any discipline for which wave or which phase of the wave light wave actually reaches to these two sources. And if we don't have that discipline, we cannot produce a alternative black and dark, white and dark pattern onto the screen. So that's the importance for two coherent sources, which essentially we can have. The formula that I ended last class with, which I can show you, that if this light source has a wavelength of lambda, if the spacing between the two gaps of the two sources is a, and the distance from the light sources and the screen, well, it's important that this alignment of the two light sources and the screen are to be parallel at all cost, at all situations. If they are not parallel, then this formula will not hold up. Although this line is not apparent to be parallel because I drew it with being less careful, but these two lines are supposed to be parallel. It has to be for the upcoming formula to be applicable. If this distance is given as capital D, and all the bright and the fringe gap or the fringe separation, আচ্ছা এখানে আরেকটা জিনিস আলাপ করা দরকার। This is pretty interesting. Fringe gap is equal to fringe separation. They both mean the exact same thing. I'll tell you why they mean the exact same thing. However, slit gap and slit separation don't make the same thing. I'll first elaborate this part so that it can make sense. A in this case is basically the distance from the center of these two gaps between the two holes. This is what we call slit separation. slit gap, or sometimes this word is also used as slit width, or sometimes you can say fringe width, actually a better term other than gap. Slit gap. Gap is not the typical term that you're gonna come across. I actually miswrote it. My bad. So might as well get rid of that. Gap is not the word. Sorry. Slit width, fringe width. So slit width means how much space is there between the opening. This is slit width, how big the slit is. Slit separation is the distance from the center to center, or if they are identical slits, it will be the distance from at least top to bottom, top to top, or bottom to bottom. That also works. Whereas, so these two things don't remain the same thing. Slit width means how big the slit is, the opening size. Slit separation means how far apart they are. Whereas for these two terms pretty much mean the same thing. I'll tell you why. If I just give you a bit of a labeling, other than giving a bit of a labeling, let me pick up a picture from the net for the double slit fringe pattern. This one is actually quite nice. There are a lot of good figures that we're gonna need for the upcoming discussion, so I might as well keep that. Okay, let me just choose this one. It's a pretty big picture. Should be helpful for our purpose. What? It's 2395 by 1798. Really? Allah jane eta kotheke asছে. Acha. If I disregard that, I can take this picture as well. This can help. Okay, better. So what I need you to understand is, you can see that this is how the brightness actually gets varied. We're going to talk about the brightness part after a slight while, so it's going to be part of our discussion. So what is happening over here, you can see that these are the bright fringes, and these are the, in between the bright, you have the dark fringes. So what is happening, this is the central maxima, which is the brightest. You can see that if we plot it over in terms of intensity axis, you can see slowly the intensity is getting lost, and slowly it is becoming smaller. The reason we say that fringe separation and fringe width, they are the same, because by definition it is meant that if this one, I mean, for example, let's say this is the center of the central maxima, this is the center of the first maxima, second maxima, third maxima, fourth maxima, so on, goes on like that. These are the bright points. So let me label them with, let's say, central maxima B0, first maxima B1, second maxima B2, third maxima B3, and B4. For the dark points, if I label them as, let's say, this is my first Descending reference or dark point, let's say D1, there is no central minima, because at the minimum, at the central position, you only have bright fringes, so there is only central maxima. There is no such thing as central minima. So the dark fringes come on top, and then D1, and then D2, and then D3. It goes on like that. By definition, the separation between two fringes means what is this gap between two bright or two dark. So I can say that this much length is what we mean as the thickness of one dark fringe. So one dark fringe starts from the center of the bright and it finishes at the center of the next bright. So you can think for this whole thing produced by individual dark fringes where they are stacked onto each other. For example, this is one dark fringe, width of a dark fringe. This is another width of a dark fringe. This is another width of a dark fringe. So in the same way, this width of dark fringes can be also said to be the fringe separation for the bright fringes, because you can see that one bright fringe to the next bright fringe is basically meant as the width of this dark fringe. So this is why fringe separation and fringe width are pretty much meant to be the same quantity, which is given as x. Whereas the slit separation and slit width are not the same thing. So if you go back to our formula right over here, the formula that leads to our observation over here, if let's say this is B0 and this is B1, I'm only labeling two things over here, and if their gap is x, the formula is given by lambda equals to ax by d. The derivation of the formula is not given to us, but this formula will be extrapolated into a more elaborate version whenever we go for diffraction grading. Couple of things that we need to pick up from this equation. I'll choose a bit thicker line. If I just do the cross multiplication of this equation, I'm gonna get lambda d equals to x, lambda d equals to x, because we know that all the variables on the same side of the equation, they are directly proportional, and all the variables on the all the variables on the opposite side of the equals to sign, they are directly proportional, where everything else is constant, and all the variables on the same side of the equals to sign, they are inversely proportional when everything else is kept constant. So typically the way we actually deal with this part is that we usually are more interested in that how does this x, or the pattern that we can see on the screen, this is affected by all these variables. So if I just try to get this proportionalities, I can write that x is proportional to, I want to write lambda, x is proportional to lambda, x is proportional to, what am I doing? X is proportional to d, and x is inversely proportional to a. This means that if we use a bigger lambda source or increase wavelength of the source, this pattern is going to become wider. If we use a bigger gap, then this pattern is going to be wider or more spread apart. And if we use smaller gap, then this pattern is going to be wider as well. So these are the three factors by which this equation works out. And that's pretty much it for the primary mathematical calculation. There are multiple things which I'm going to discuss after a while, but before I get into that, if you have any question, yes, Zara, go ahead.
Sir, একটু ফ্রিঞ্জের পিকচারটা নিয়ে যাবেন একটু। হ্যাঁ স্যার, তো এখানে B0 নিচে যে ডার্ক ফ্রিঞ্জটা আছে ওইটা কি হবে?
Well, this is also D1. Let me write. B0 নিচে যে dark fringe আছে, this will be also D1, but this is on the lower side, because this entire fringe pattern is mirrored about the central maximum portion. So central maximum উপরে যা আছে নিচে হুহু তাই থাকবে. So this is also called D1, and this is also called B1. So you have the same thing going down exactly the earlier way. This is D2 and this is B2 and so on and so forth.
আচ্ছা
বুঝছো?
জি স্যার।
Achha. So and one more small thing I would like to remember is that at the points where we have the bright locations or bright fringes, where we have constitutive interferences, the pad difference is n lambda, and at the locations where we have destructive interferences or dark points, the pad difference is n plus half lambda. It is this half that makes the whole phase difference go with 180 degree. So here the value of n is given by 0, 1, 2, 3, ইত্যাদি. So central maximum জন্য n equals to 0. First dark fringe জন্য n equals to 0. So at this point, where is this? At this point, the pad difference is 0 lambda. At these 2 points, D1 and D1, the pad difference is half lambda each. So এখানে আমাদের pad difference half lambda, এখানে আমাদের pad difference half lambda, and this slowly goes in incremental order. This is for the bright fringes, and this is for the dark fringes. Is that half lambda, which is relevant to 180 degree phase angle, that causes the phase to go out of against each other, and the merging gives us zero intensity or zero brightness of the light rays. Acha, এই হচ্ছে এই formulaটার part. The next part that we're going to cover is that what is going to happen. Then the next part is going to be covered about light waves. Is that you can see that whenever we are working with a double slit experiment with light waves, the intensity is not equal everywhere. If you wonder why the intensity is not equal everywhere, you can see that the intensity is slowly becoming dimmer as we are slowly getting farther away from the central maxima. There is a reason for this. Intensity of at any location of a light source is given by three different factors. Intensity is proportional to frequency squared, intensity is proportional to amplitude squared, and intensity is proportional to 1 upon distance squared. So frequency in this case is a practically fixed variable because we are not essentially changing the source for one specific pattern. We're going to keep the frequency fixed. Amplitude is the primary variable for which we are having brights and darks. At the constructive points, the amplitudes are getting added. For example, for each of these constructive points, the two amplitude from the sources A1 plus A2 are getting added. If you wonder where is A1 and A2, let's say this is our source 1, this is our source 2. So let's say the amplitude reaching up to this screen point is A1 and then that coming from the slit 2 is A2. So for the constructive points, this is getting added, and the destructive points, it is getting differenced is a word, differentiated is no, differenced. What I mean is that we are going to give A1 minus A2, I'm going to give a modulus because this is not going to be a negative quantity because we're talking about the absolute value of the amplitude that is remaining. So this is what is happening in the destructive point, this is what is happening in the constructive points. Now, interesting factor, if you try to visualize for a normal slit pattern, if I just take up one figure, maybe let's say I'd like to have okay, this is actually a good figure. Nice one. Load out, copy image. This is actually one of those figures where you can actually see where these things are properly labeled. So S1, S2, general setup, 10 waves are coming in. These black lines are the points to which the bright dots are produced, and D are the points where the destructive, or we have the dark points. So B are the brights, D are the darks. B means constructive interference, D means destructive interference. This is a nice figure. So what I need you to want you to understand, the length of path that light waves actually have to cover, let's say to reach from here to here and reach from here to here, is something. But if you consider this bright point right over here, I'm taking this extreme point to give you a better visualization. If you consider that path, let me label that with green, the length that the individual light waves have to travel from the two sources is far longer. Do you see that these two lengths are smaller and these two lengths are much longer? Do you see that visibly? Everyone?
Yes.
So
Yes.
the point, thank you. The point I'm going to make is that the farther we will be observing away from the central maxima, light rays from the two individual sources have to travel a much longer path. This brings us to this relationship that I just wrote a bit earlier, that I is proportional to 1 upon D squared, which means the farther the light rays have to travel, the intensity will become low in the inverse proportion of the distance squared. That's why farther points will always be less bright compared to the central point. This is exactly why we have a pattern like this, that as we go further away from the source, the maximas are not as bright as the central maxima. Central maxima will always be your brightest maxima, and as you go further away, your maximas will slowly lose brightness. There comes another question as well. You might wonder, why is it not in that case that the minimas are becoming or remaining all black? Why should the minimas all remain black? Shouldn't the minimas also represent some of the other parts?
Sir, can you repeat the question?
Just a second. Hey Farhan, kon Farhan? Achha Farhan, I got your message. Messenger me after 10 p.m. We might have a small bit of discussion about how this could be processed. What has happened has happened, but I'll help you take care of the problem. Okay, sir?
Okay, sir.
Works. So the question is that, I mean, you can see over here that as we go further away from the central maxima above or below, you can see that the bright fringes are slowly losing their brightness. which makes sense, which I described over here, that further distance is causing them to lose brightness. What about for the dark fringes? Apparently all the dark fringes are remaining exactly dark. How about that? Why? Dark fringes are not becoming brighter. What I mean is that here you can see perfect darkness, and here you can see also perfect darkness. Here you can see perfect darkness as well. So what is happening? Questionটা কি বুঝছো? Why the
Yes,
dark
sir.
fringes are unaffected by the distance factor, where the bright fringes are affected by the distance factor? That's my question in small terms.
Sir,
Yes.
can you go back to that picture that you have below, where you were like showing the pathways? Yeah, act a second to that.
Are you trying to draw this?
No, sir, I'm trying to like get the whole thing.
Oh, sure, sure.
I was just
Do not preferably try to draw this, because you will be never required to even draw this many waveforms in your actual exam. They might as well give you these printed waveforms. You might be asked to draw these lines, which I've shown you in last class for one of the question, that you might be asked to draw these lines. So don't bother to draw all these parts. So I'll answer the question. The question was, why is it that the bright fringes are affected by the distance factor right over here, but the dark fringes are not affected by distance factor? To make a better sense, let me tell you what is happening here. Then I'm going to give you some numerical values to make a much better comprehensive idea. The reason the dark fringes are remaining unaffected, or dark fringes are always remaining dark, because they come from the subtraction result of the two individual waves amplitude at that position, whereas the bright fringes work by the addition. Here's the deal. Try to understand. Let's say the amount of light, the amplitude of light that reaches at the central maxima from the two sources, they are both 5 plus 5. So you're getting a total amplitude of 10. So you're getting a pretty bright interference. Let's say on this second point, you are getting maybe how much? Let's say 4 plus 4. And let's say over here, you're getting 3 plus 3. I mean, I'm showing you uniform decrease. It's not usually uniform, but just to make sense. So are you understanding what I'm trying to show you here? That the individual amplitude coming from the two sources, that is becoming small. So the sum is becoming small. Essentially, the intensity is also becoming less bright. What is happening to the dark fringes? Let's say in these dark fringes, the difference is going to be 4.5 minus 4.5. Both of them has decreased, but they have decreased by the same amount. So what is happening to the subtraction result? Is it still remaining 0? Or is it becoming something else?
still remaining 0.
Remaining 0. For these dark fringes, maybe both of them has become 3.5 minus 3.5. They have both decreased, but they have decreased by the same amount. So as a result, the result is still remaining 0. So the zeros are pretty much remaining 0, because they have both experienced reduction by approximately the same amount. That's why the dark fringes are still remaining perfectly dark, but the bright fringes are actually becoming less bright. Does this make sense?
Yes, sir, it does.
Yes, sir. The wave from S1 travels a little bit more than a wave from S. Travels a little less than wave from S2, right? Like
Exactly.
green. Yeah. So would the amplitudes be like from both of the waves be
Exactly
same?
same.
Why?
Okay, I'll tell you. I have written equal numbers over here just to give you a rough idea, but it is always true that the wave that individually travels the shorter way will have a slightly bigger amplitude compared to the other one. So here's what I can tell you. In true case, this might as well be like, let's say maybe 3.1 plus 3.0. The difference between the amplitude of these two light waves would be really close, but not exactly same. That's true. That's essentially true. This effect is more or less not so significant for light waves, but this effect is extremely significant for sound wave. We're going to see about the effect of the sound wave after a while, where we'll be replacing these two slits by two identical loudspeakers operated from the same source. So we'll see about that. But for the light waves, this difference effect actually makes too much of a less effect. I mean, if you think for in terms of percentage difference of the variation of these two individual amplitudes, that is actually quite small.
But then it should mean that the dark fringes are getting a little less dark as you move away. If it's probably not perceivable, but
It wouldn't be perceivable, but if you think when a precise mathematics, yes.
okay. Yeah.
Yes, sure. But good pick on that one. The next thing, before I get into the next thing, I'd like to show you what happens to the sound waves as per your books. That if we do the similar experiment using two loudspeaker apparatus setup. So let me show you a setup for that by loudspeaker.
So sir,
জি
তাহলে কি dark fringes গুলো আসলে less dark হচ্ছে?
No, that for the light in mathematical terms, yes. In observation terms, no. I mean, to tell the truth, this thing would not exactly be 100% dark, because if you think precisely, the length of the light wave that this thing is traveling and the length of the light wave this thing is traveling, they are not essentially exactly the same length of path, because this is traveling a bit shorter, this is traveling a bit more. So these two numbers are not supposed to be equal in mathematical terms, but the difference of these two numbers for light waves is going to be so small that we would not be able to see any light over here. For example, if I show you one of the images, this is actually a computer generated image, not essentially a photograph. If I show you a photograph like this is the type of fringes that we usually get. Now you might actually see that between these small dots, we have even larger dots. What is happening in this thing? This is basically this part. I mean, if you have a look over here, I'll give it some time to become clearer. Come clearer. Or is this not becoming clearer? All right. So what happens if we have only one slit? I mean, if we don't have the second row, we usually get a pattern like this. We get uniform up and down like this for a single slit pattern. But if we have a double slit, in all of those individual patterns, we get multiple slits. So we are talking about the double slit pattern. Why double slit pattern is interesting for us? Because whenever we give a single slit, the wavefronts actually gets diffracted, and that produces this pattern. This is an explanation that I personally don't know very well, that why the wave behaves like this. But what happens for the single slit pattern behavior is also seen on the double slit pattern as well. You can see that, you can visibly see that there is a significant similarity for the brightness parts. But what we are essentially discussing for your content for the double slit experiment, we're talking about the gap between this center of this bright line and this dark line, bright line, dark line, bright line, dark line. We're talking about this amount of specification. So here the single slit pattern was shown for the center part. Here is the double slit pattern for the center part. So each of these bright lines are pretty much aimed as the bright location. But the question that you just asked, that should these lines not be perfectly dark? They are not going to be perfectly dark. For example, if I switch the light source off, the amount of darkness should I be getting here is not essentially equal to the amount of darkness that I'm getting right over here. These lines are to some extent bright, but that would not be by a huge
Observed
margin.
by us? Would that be observed by us?
We can see the effect, but that is considered to be, I mean, for light waves, the amount of intensity variation is actually really, really small.
Okay, sir.
Okay. the following thing that I was trying to get at is that I was trying to search something here, double slit pattern, slit fringe pattern for sound waves. Okay, I might actually save this thing, duplicate. Okay. Don't. Okay, yes. This is the typical apparatus setup that you are mostly questioned by. So let me explain what is happening here. We have two identical speakers. They are run from a single audio signal generator. So this audio signal generator is a device that can produce a known frequency of sound. So it's going to produce a frequency signal to those loudspeakers, and these loudspeakers are going to play that tone. Tone means a single frequency sound. Uh, so let's say if this thing is calibrated at maybe 200 hertz, then both of these loudspeakers are going to play at 200 hertz. The distance between the in-between centers is 1.5 meter. And because we are working with sound waves, we are not, we don't have to divide it from a single source into two opposite sources, because sound waves essentially are a mechanical wave, and they are affected by a lot by the medium. And to observe the loud and silence, we cannot use a visual pattern over here. Rather than that, what we're doing, we have a microphone and we have a stick attached to this. I mean, this apparatus could be vertical, this apparatus could be horizontal, doesn't matter. I mean, we might as well place them horizontally on the table. And then we're going to move this microphone along a line that will be perfectly parallel to the setup of these two things. So we're going to move this microphone, keeping this 2 meter distance uniform, and we can move this microphone. This microphone is connected to a CRO. And interesting enough, pretty much like the earlier way that we have explained, in this CRO we'll be able to say loud sound and we'll be able to say quiet sound. So as we are going to move this microphone, for certain position of the microphone, this CRO is going to give us high intensity, and for certain position of the microphone is going to give us almost zero intensity. Almost, I'm using the word almost because it's not going to be perfectly quiet, because there is always some ambient sound that we cannot get rid of. Now, interesting enough, what is the positions where we're going to get loud sounds pretty much represent the concentrated interferences or pad difference of n lambda, and positions where we're going to get the destructive interferences or quiet sounds represent the pad difference for n plus half lambda, or represents the destructive interference. However, if we do observe the intensity pattern for sound waves, that is slightly different compared to what happens to the light waves. এইটার একটা figure comparison মনে হয় তোমাদের নোটসে দেওয়া আছে. I'd like to find out the note. Please be there. Okay, yeah. So this is the typical intensity pattern observed for light waves. We have this kind of variation, and in some cases we can also have this shape available. This is the shape that is most commonly associated for sound waves. There are multiple reasons for this. One of the primary reasons is that we cannot essentially produce sound waves from point sources like light. For example, this figure that I just showed you, this one, we have to have vivid sources. Now, because we have vivid sources means it's a large enough source for us to be able to detect some measurable sound over here. Because we cannot essentially work with very small loudspeaker mechanism and place the microphone pretty far apart and expect the apparatus to work, because we have to have the sound spreading out in both directions in a wide angle, so that this microphone is actually receiving effective sound waves from both of these sources. So they have to be quite loud. They don't have to be as big as like professional mics, but they cannot be as small as like a এক পয়সা coin. এক পয়সা তো না মানে এক টাকা কয়েন, they have to be significantly large, like so because these sources are quite large. Whenever you consider any of the points which is supposed to be a perfect destructive interference, from center to center you might as well get a pad difference of perfectly n plus half lambda. So what I'm trying to mean, I would like to actually show this with a sound wave. Let me figure this out. Hold up. Okay, I might be able to work with this figure. দেখাই দিছি আমি, একটু সবুর করো। Okay, I have this one. Then I'm gonna snap this picture. Paste it. Transparent selection. And central maxima. I think this will work for our purpose. Do you guys understand what I'm trying to achieve here? Central maxima should be represented by the highest maxima, and
Yes.
second maxima is over at this point. So all the in-between points should give us quieter sounds. Now let me show you what is happening. You can see that nowhere this sound level for this, the microphone is going to be moved along this line, and these two loudspeakers are operated by the same frequency source. So along this line, along the green dotted lines, we are having the maximas, and for the blue crosses, we are having the minimas. We are expecting them to be minimas. So they have given loud and they have given soft. It is not silence. It is a soft sound, or you can say it is the softest sound. How can we detect it in the CRO? I'll tell you this after a while. So what is actually happening? This is the point where the measured pad difference between the two sources is absolutely zero. Pad difference zero means you have the biggest amount of merge, you have the most amount of sound. However, whenever this point is considered, whenever the microphone head is placed in this position, the distance from the center of the loudspeaker and the center of the loudspeaker, for example, the distance of the difference of these two distances, let me label them with red, the distance of these two distances is actually half lambda. But the problem is that the loudspeaker is not essentially a single point object. You have to understand that sound will essentially reach to this loudspeaker, let me use orange, from this corner. Sound will be receiving this point from this corner. Sound will be reaching this point from this corner and all the way up to this corner as well. So sound is actually receiving this point from two vivid sources. So you cannot have absolutely perfectly destructive scenario because you are delivered with a lot of incompatible phase difference waves because of the pad differences being so varied, because the objects or the sources themselves are quite wide. They are large enough sources. So you cannot get a perfect cancellation. Do you get my point?
Yes, sir.
So what if the loudspeakers were small?
What is the loudspeaker?
What if they were small, like smaller in size?
If the loudspeakers were small, then we would have to use an extremely sensitive microphone. Might be very difficult to achieve in a laboratory. / do this experiment in a sound studio where you don't have any effect of the ambient sound, so that all the sounds can be properly obtained. Or we could use a really loud loudspeaker and could use small cardboard slits, and then we can also attempt to perform this experiment as well. That might also give us a loud sound. But the thing is, as long as we are considering two sources which have some spatial arrangement, which means they are not of zero size. They have some width so that the physical sound waves can travel through. This effect can never be altogether get rid of. We cannot altogether get rid of this factor. I mean, what I'm trying to tell you is that for the light wave, we would have some difference at this point, but that difference is considered negligible. But for sound wave, this difference cannot be considered negligible. That is the key difference that I'm trying to tell you. Do you understand?
Yes, sir.
Zara, তোমার question answer পাইছো? If we
Ji,
could
sir.
perform this experiment in a very quiet room with very small loudspeakers with even high volume, it might be possible to achieve that. We might actually get a perfect quiet sound over here. But achieving this would be pretty difficult for a regular laboratory. However, the reason that I'm trying to tell you that because these two loudspeakers are wide objects, sound would be received from this point, from all of these multiple different points. So we cannot get perfect cancellation. This is the reason we are never getting perfect silence over here. Similarly, over here, we are having attenuation. So we are having the reduction of the intensity for the next louder point. And over here, we are having even less cancellation because you can see that this was more quiet. This is even less quiet because here it is much more close to the zero x-axis. This is even far high above. So what is the difference between this curve and that curve? I want you to appreciate this. You see that for the light wave, only the peaks are decreasing, but all the dark points are labeled as perfect zero. But for the sound wave, the peaks are decreasing, correct, true. The peaks are coming down, but also the bottoms are also rising up. How this can be seen in the CRO? For example, if the figure that I showed you over here, কই গেল? যে এখানে একটা ফিগার ছিল, কপি করে নেই কেন আমি? তো ফিগারটা গেল কই? Apparatus Setup একটা ফিগার ছিল যে। Oh no, what have I done? This was stupid.
Sir, উপরে ফেলে আসুন নাই তো।
হ্যাঁ? আচ্ছা, never mind. এই Apparatus Setup একটা ফিগার ছিল না, ওই Apparatus Setup ফিগারটা কই জানি চলে গেছে। ওই যে দুইটা লাউড স্পিকার পাশাপাশি ছিল যে, ওই ফিগারটা খুঁজছি আবার। I did not copy that by mistake. And I'm
অন্য কোনো ট্যাব চেক করতে পারেন।
I did. I see. Got it. So what is going to be seen in this CRO screen as we are going to move this microphone along this line, which has to be predetermined, or we might as well place a meter rule along that line, or we might actually draw a line on the table that we're going to move this microphone along this line to make sure that this moving line of the microphone is perfectly parallel with the faces of the loudspeaker. So you have to make sure of that. The CRO is going to behave like this. Let's say whenever you are the microphone is placed over here inside the CRO screen, we're going to see the biggest amount of vibration. For example, we're going to see a really loud wave. As we're going to move the microphone, let's say from here to here, this is going to become really, really small. For example, let's say, let me give points. Let's say this is 0.1, 0.2, 0.3. So let's say this is the situation for 0.1. And this is, let's say, the center line. At 0.2, you're going to get a pretty quiet sound, but it's not going to be absolutely zero. So you might actually have a sound that looks maybe somewhat like this. So you would have some vibration remaining, but not perfectly zero. You're not going to get silence. You're going to get a soft sound. And the way we'll be able to determine the physical position of this sound is that whenever we'll be moving the microphone from position 1 to position 2, we'll see that this amplitude is slowly decreasing. And there would come a point, if we go past the 0.2, then it will start to increase again. So you have to find out the minimum, the point where that amplitude is minimum or the smallest. That smallest location basically shows you where the pad difference is 0.5 lambda. So it will not be perfectly zero, but on the CRO screen, you'll be seeing a continuous decrease. And then after the decrease got finished, you will see it increasing again. So this is what is going to happen. And in position 3, we're going to get a smaller wave than position 1. Maybe we're going to get a smaller wave than position 1, maybe a wave this much big. Maybe we're going to get a wave this much big over here for position number 3. Then if I assume that there is a position number 4 over here, in the position number 4, this is actually louder than position number 2. Have a look. This has a much higher height. This is a much smaller height. So position number 4 will give you a, so this is 1, this was 2, this is 3, and position number 4 will be somewhat above than position number 2 that we got. So this might as well, let me draw with blue maybe. Position number 4 would be a bit more louder than position number 2. That's what we're going to see on the CRO screen.
Sir, I mean, a part the position number 4. Why will it be like louder than position number 2?
Because first of all, number 1, the primary problem of this experiment is ambient sound. The second problem is that here the sounds would eventually reach up over here, and the cancellation effect would be far too less compared to what happened as cancellation over here. Because here the two sound waves would be pretty close to each other because the pad differences would be far more. So here the pad difference was assumed to be 0.5 lambda. Here the pad difference is supposed to be 1.5 lambda. For such a bigger pad difference, so you do understand that whenever this sound would eventually reach to point number 4, this, how can I put this? These sounds would merge with each other, but the difference that they will be bringing from the sides of the loudspeakers are supposed to be even bigger compared to over here, because here the difference was supposed to be 0.5 lambda for the two individual waves that is coming from, but here the wave difference is supposed to be how much? 1.5 lambda. Eta to buঝছো?
Gee, sir.
Now, because they are wide sources, let me put it this way. Let's say the variation that you're gonna get for the size of these two things is gonna be 0.5 lambda plus minus, let's say 10%. So you're gonna have a variation. Here you're gonna have 1.5 lambda plus minus 10%. So the amount of variation is even more, which means the destructive effect would be more weakened. Because the pad difference of 1.5 lambda and 10% difference of these of this bigger quantity would ultimately result in a much bigger range of wavelengths. So let's say here for this location, the two sound waves were overlapped by almost two identical and opposite waves, but maybe let's say how can I say, in terms of their amplitude variation, maybe only 0.5 or 10% কত হয়?
Sure.
0.05. Maybe only 0.05 segments was different. So you didn't get perfect destructive. But whenever for the second destructive point, this amount of plus minus variation for 10% of 1.5 lambda amount, this is going to be even bigger compared to what is the difference over here. So I mean, if you think for the absolute value over here, I mean, let's say 0.5 lambda, our handwriting and also so this is 0.5 lambda for the first destructive point plus minus something, and here for the second destructive point, let's say 1.5 lambda plus minus, let's say something. This is supposed to be bigger compared to this one, right?
Yes, sir.
Because this is the pad difference itself was much bigger, which means here the mismatching of the destructive interference phase would be even bigger. So the amount of destructive effect you could achieve over here, you wouldn't be able to achieve that much destructive effect right up over here. আমি ভুলে এখানে দেখাইতেছিলাম এতক্ষণ, এটা actually এখানে হবে, এটা তো আরেকটা কনস্ট্রাকটিভ, sorry. So you would have less destructive effect compared to what happened earlier, because the difference of the two waves would be even more.
এটা কি ওয়েভলেন্থের জন্য হচ্ছে নাকি অ্যাম্পলিটিউডের জন্য হচ্ছে?
wavelength difference is causing what is going to happen. The difference is happening because of amplitude and also because of the size of the loudspeakers.
Okay.
I mean, are we going to have constructive or destructive or constructive or destructive? That is dependent upon the lambda. But how much should it happen is depending upon how matching these two things are, the two incoming waves are, or how mismatched those two waves are. If the waves are really matching, then you can get really good constructive, really good destructive, and so on and so forth. But if the waves are sort of mismatching, then you are not going to get as good constructive or destructive effect. So these reasons would never be asked to you, but in many cases, what they actually give you is that what is the typical shape of intensity versus distance for the sound wave, and what is the typical shape that for intensity versus distance for the light waves. These are two different shapes that you have to remember. That for light waves, all the minimas are considered perfectly zero because the difference would be immeasurable or too small, minuscule, negligible, however you take it. But for the sound waves, the maximas go down and the minimas go up. So the sound is become, I mean, more or less, I mean, if you go further down the line, eventually this will become a horizontal line, much above a flat line above this thing. And this is basically this part of the sound which remains in our microphone, even if you go pretty far away, is what you call the ambient sound. Ambient sound means basically the noise of that surrounding. You cannot get a perfect quiet room unless you perform this experiment in a sound studio.
স্যার এই লাইনটা তো পুরোপুরি কখনোই হরাইজন্টাল হবে না, তাই না?
No, this will actually become horizontal. Horizontal হওয়া মানে কি? মনে করো হচ্ছে মাইক্রোফোনটাকে যদি আমরা এই লাইন বরাবর মুভ করতে 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 অনেক দূরে নিয়ে যাই, should we ever get a perfect zero reading?
না।
We would get a perfect zero reading if there was no sound in our environment. You cannot think of that kind of an environment in an earthly place unless you artificially create it. That's what I mean by the ambient sound. This is sort of like the background count error in a radioactivity experiment, similar to that, but not identical, but similar to that. I mean, this is something that you cannot get rid of unless you specially design your environment to get rid of that.
No, sir, if we just like ignore the ambient sound, তাহলে তো we would like get a horizontal line, won't we?
Yes, yes. No. We would get, if we ignore the ambient sound, or if we do this experiment in a sound studio, we might get a line that actually merges with the x-axis. I mean, this line would eventually come to zero. You're not going to get any more sound.
Yes.
We're going to get a horizontal line anyway. If there is ambient sound, it will be above the x-axis. If there is no ambient sound, this will be aligned with the x-axis.
Sir, like ambient sound or like background noise, it doesn't make it. Can I correct for that? মানে যেমন background count rate, radioactive experiment আমরা যেমন মানে ওটাকে করে দেই। এখানে ওটা করা সম্ভব না?
I believe yes. I believe yes because I mean, I strongly believe it is possible, but I do not know the exact technology for this. But I'll tell you why I believe it is possible. Think about this scenario. Let's say a certain band, rock band, is performing on stage. So they are going through the instruments, they are doing bass and drum, and they're screaming in their microphones. But to get a really nice output for the audience, you need to have those individual input of those microphones and the sensors not affected by the other sounds, right? Because if all the equipment pick up the noise from the other sources, then you'll get a hodgepodge of noises. So there is definitely a way by which noise cancellation is done for each of these individual input devices or capture devices. So this is definitely possible, and I believe we human beings have definitely developed that. But I honestly don't know the actual underlying principle or mechanism for that. But I strongly believe that yes, it can be done.
Sir.
Yes.
আমি এই জায়গাটা এখন confused. যদি আমরা ambient sound counter করি, why will the line be horizontal? Why will it be parallel to x-axis? Like why will we get a line forming out of nowhere?
Because you would not get an environment in a regular atmospheric situation where there is absolutely no sound. Things are always vibrating around us, either in the subsonic level or in the supersonic level.
হ্যাঁ তো স্যার এই জন্য একটু হলেও তো মানে কি বলবো, একটু হলেও তো ওয়েভই থাকবে লাইনটা, রাইট? Maybe we cannot observe it with our eyes, but
Here's the deal.
একটু হলেও তো থাকবে।
Here's the deal. Having the line wavy means you are having a periodic, this is distance. This microphone being placed over here, this is intensity, this is not amplitude, this is not displacement, this is not the sound wave, this is the sound wave. This is how much amplitude is observed over distance away from the central maxima. বুঝতেছো কি বলতেছে? You are expecting that this line would be a bit curved because there will be some sound. এটা না তোমার proposition.
জি স্যার।
But this is not measuring the sound, this is measuring the intensity of the sound or volume. The actual sound is measured in the zero. How much is that amplitude that is represented in this curve? Intensity variation means হচ্ছে কোনটা সার্টেন জায়গাতে এরকম পিরিয়ডিক্যালি সাউন্ড ভলিউম বাড়া কমা, এটা তো ন্যাচারালি অ্যাভেলেবল হবে না।
আচ্ছা স্যার,
এখনো বুঝো নাই?
কিছুটা বুঝেছি।
This intensity means how much sound do you have, is the amount of sound that you have, or is the intensity of the sound or the energy of the sound that you're having that is periodically changing over time or not? Are you having a varied amount of intensity of sound, or are you having loud and quiet, are you having that variation or not? If you go pretty far away
আচ্ছা স্যার, বুঝেছি।
you're going to get a continuous ambient sound, which is basically the natural sound that exists in any environment.
বুঝেছি স্যার, থ্যাংক ইউ স্যার।
আচ্ছা ঠিক আছে। So this is the part that I was trying to get at for this part of the discussion. The next thing that I'm going to discuss is that what's going to happen to these light source intensities if we start to work with these slit gaps. If we sort of change or change these slit gap to na এটাকে জানি কি slit widths. If slit widths গুলো যদি আমরা অপারেট করা শুরু করি তখন কি হবে? Let me show you. For a light source, let's say these are the two slits. Currently they have the same slit width, which means they're of the same size. And this is our central maxima line. This is our central maxima line. Wow, this came out, no, not very horizontal. So this is central maxima line, and let's say this is our screen. Let's say this is our screen. If we have two slits of perfectly equal slit width, then they are going to produce the same amount of amplitude out of them, because equal amount of light should be able to pass through them. Let's say this is our source 1, this is our source 2, so they are giving up equal amount. So this pattern for this apparatus, bright points are bright and dark points are dark. Now let me just give you some idea. Let's say this is our central maxima. Here we have A plus A, and this is our first darkness. This is A minus A. I'm only considering these 2 points just to avoid confusion. So we are having perfect brightness over here, the most bright situation over here. We are having perfect darkness over here. Beautiful. What if we now keep the slit separation same? We're going to keep the slit separation same. Keeping the slit separation same means we're going to keep the center to center distance exactly equal, but we're going to make one slit bigger. So if we want to make one slit slightly bigger, we just need to make this hole slightly bigger on both sides. এখানে এদিকে একটু বড় করে দিলাম, নিচের দিকে একটু বড় করে দিলাম, যাতে করে আমাদের সেন্টারটা সেম পজিশন থাকে. So the A is kept constant. As a result, the pattern would pretty much remain the same, but this would essentially affect our brightness. The question is, if we increase the slit width of one of the slits, how would this affect our pattern? Now what's going to happen for this change scenario? This for the bright fringe location, we're not going to have equal amplitudes coming in. Let's say currently this one is delivering you at this point an amplitude of A plus A, because if you wonder Why this should be bigger? Because whenever you have a bigger hole size, bigger portion of the wavefronts can pass through, which means more energy can penetrate through that hole, which means the ultimate delivery of the energy through this hole would be even bigger. This is basically talking about that if you have a small cover onto, this is something like the aperture of a camera. If you make the aperture bigger, you expose the film for a longer duration of time, you take a brighter picture, and vice versa. Or like for our eyes, it is something sort of like the pupil or the hole inside the at the center of the choroid, so that at night, whenever you're trying to see in dark, this whole pupil becomes large, dilated, so that you can get more light to process information. But whenever you're in bright sunlight, then pupil becomes small, so that we do not damage our retina cells. So in this case, for this scenario, change scenario, the bright points, this point is gonna get something bigger than A. For example, this is giving us A plus A, and the original A was also coming in. So together, now the total amplitude at the bright central maxima would be somewhat bigger. So this will make the bright fringes brighter. Do you understand this part?
Yes, sir.
Because bright fringes become brighter. And what happens for the dark fringes? So I'm gonna give a bit dotted line over here. Here, this will be A plus A minus A, which gives us the smaller remaining, which means earlier this used to be 0, but now we have some amplitude remaining, which means the dark fringes will also become slightly brighter, which means for this scenario, all the dark fringes will not be perfectly dark, which means if you observe this graph, if you observe this graph, in this case, this entire red lines, let me copy this so that it's easier for me to work with. So initially, whenever both of them are exactly of equal size, when they're exactly of equal size, we had this pattern. I'm actually placing it over here. But whenever we have made one of the slit become slightly bigger, the bright fringes will become brighter, and the dark fringes will also become slightly brighter, which means you are not going to get perfectly dark, which means all of these peaks will rise up a little bit, and this entire part of the dark fringes which are touching the horizontal axis will not touch the axis anymore, which so that I can show maybe by taking this image and moving it a bit up. You're going to have a figure that's going to be somewhat like this. So all the bright fringes will become slightly brighter, and all the dark fringes will also become slightly brighter, because you cannot have perfect cancellation. A graphic manipulation to bujha geche?
Yes.
Everyone? Acha. Next scenario, I'm gonna draw this with green. Other than increasing the slit size, so I'm gonna now cover this slit, bring up the slit to the same size. Let's say now I have both the slits of the same size, so initial conditions are same. If we make one of the slits smaller, which means, let's say now I'm going to make this slit not smaller than the original size. So let's say I actually have to draw the line once again, other than I cannot do this. So thickness, okay. Let's say now I'm gonna make a very small size slit right here. I'm keeping the gap equal, but now I have made the slit slightly smaller. Can everybody see that this is slightly smaller than this one? Can you see that? I mean, this is slightly bigger.
Yes, sir.
Okay. So what's
Yes,
going to
sir.
happen? If this one is giving us an amplitude of A, the light coming out from this one would be slightly smaller. So this source's amplitude would be A minus A. So the new information I'm writing with, let's say red, because I don't want to erase this, because I would like you to compare. So now the new amplitude is going to be A minus A. So what will happen for the bright fringe? For the bright fringe, we're going to have A minus A plus A. So together we're going to get twice A minus A. Earlier we used to get perfectly 2A. Now we're going to get something smaller. So the bright fringes will become less bright, because the total amplitude has become somewhat smaller than before. Make sense?
জি স্যার।
বলুন, দেখো না বুঝলে আমাকে কোশ্চেন করো। However,
আচ্ছা স্যার,
yes,
সরি স্যার।
না
স্যার
বলো।
যদি মানে নিচের স্লিটটার মধ্যে আমরা গ্যাপটা ছোট করতাম আর উপরেরটার সাথে যদি গ্যাপটা বড় করতাম তাহলে তো সেম ইফেক্টই হতো, রাইট?
আবার বলো, বুঝি নাই।
স্যার এখন তো আমরা হচ্ছে গিয়ে নিচের স্লিটটা হচ্ছে গিয়ে বড় করছি আর উপরেরটা ছোট করছি। যদি আমরা উল্টাটা করতাম তাহলে তো ইফেক্ট একই থাকতো।
Acha, I understand your question, but I'm gonna cover the simultaneous change of both একটু পরে। আগে one
Alright,
change
sir.
at a time টা আলাপ করে নেই, then I'm gonna get to that. Don't worry, I'll discuss that. Acha, coming back. So here the bright fringes will have a bit less brightness compared to the original condition, and what happens to the dark fringes? So if you consider try to calculate for the dark fringes, this would be A minus A minus A. So because there is a modulus over here, there is a modulus over here. So this would be ultimately A, which means some light would still be remaining, which means you cannot do perfect cancellation, which means for this case as well, the dark fringes will become somewhat bright. বুঝি নাই আমি, আরেকবার বলো বাবা।
যে ওই লেন্সটা আপনি কমিয়ে দিলেন না, ওই যে ছোট্ট ওই যে জায়গাটা, আপনি কি হলো আমার নেটে প্রবলেম হচ্ছে।
আচ্ছা, তুমি তাহলে কোশ্চেনটা একটু আমাদের অল চ্যাটে লেখো for everyone so that I can discuss with you. I could explain that as well. Don't worry.
সমস্যা নেই, আমি ভিডিও দিতে পারবো, আমার আসলে নেটে প্রবলেম হচ্ছে।
Acha, I'm sorry. So what is happening if we now observe for the sum of the amplitudes for the dark fringes, we are going to see that we still have a certain amount of light remaining. So earlier which used to be 0, but now we have something remaining, which means the dark fringes will become brighter. So if I write this whole thing, this is how it's going to look like. I'm writing to make sense with you. Increasing slit width of one slit makes bright fringes brighter, dark fringes brighter. This is basically good. Decreasing, I might as well choose a bit thicker line. Slit width of one slit makes bright fringes darker, bright fringes darker na likhe dimmer likhi, this is a better word. Bright fringes will become dimmer, but dark fringes will become brighter. এই জিনিসটা বুঝছো কিনা দেখো। একটা সার্টেন স্লিটের স্লিট উইথ কমাই দিলেও আমাদের ডার্ক ফ্রিঞ্জেস ব্রাইট হচ্ছে। এটার কারণটা হচ্ছে ডার্ক ফ্রিঞ্জেস পারফেক্টলি ডার্ক হইতো যখন দুইটা সোর্সের অ্যামপ্লিটিউড রিসিভড এক্স্যাক্টলি সেম হইতো, সো দ্যাট দ্য সাবট্রাকশন রেজাল্ট উড বি 0. whenever there is a mismatching situation, either একটা বড় একটা ছোট অথবা একটা ছোট একটা বড়, the subtraction result will not be perfectly 0, which means some light will be remaining. Whenever some light is remaining, it will be definitely brighter than 0. So this is the important part that you need to understand, that these two things are not same. Increasing the slit width of one slit makes both of them brighter, which is logically acceptable because the sum becomes more than 1. Decreasing the slit width will make the bright fringes dimmer because the total sum will become smaller. However, the dark fringes will become brighter because the difference will be non-zero. এই ডিসকাশনটুকু বুঝা গেছে কিনা?
Yes, sir.
এই পার্টটুকু
জি
সবার কাছে
স্যার।
ক্লিয়ার হয়েছে যে কেন এরকম হবে? আচ্ছা, যারা একটা কোশ্চেন করছো, সো আমি যদি এই সিনারিওটার যে এই সিনারিওটার গ্রাফ যদি এখানে আঁকতে চাই, সেই গ্রাফটা দেখতে কেমন হবে? Let me copy this up and try to do this for you. Might not as well be very beautiful, but I'll try. So bright fringes will become dimmer and dark fringes will become brighter, which means in this case, this entire pattern will rise above the x-axis because they're going to become slightly brighter. However, all the peaks will also lose their maximum value, so the whole pattern will become somewhat squashed. The bright fringes have become somewhat dimmer, but the dark fringes have become somewhat brighter. So you're not going to get perfect darkness anywhere, but you're definitely going to get that pattern like bright dark, bright dark, bright dark, but some light would be remaining in the likely zero places. Make sense? So far?
Yes, sir.
জি স্যার।
দেখো
Sir.
নাম্বার কোশ্চেন করো। Yes.
Sir, আমাকে এই পার্টটা আরেকবার বোঝাবেন যে এই যে মিনিমাস গুলো এগুলা সবসময় মানে সবগুলো একসাথে একটা লাইনকে কেন টাচ করছে?
Because for light waves, we consider the difference of the individual path length covered is extremely small. Or in other terms, I can say that whenever light rays would actually reach at one of the likely destructive points, their individual amplitudes would be nearly equal to each other, or the difference between their individual amplitudes would be immeasurably small. So they will usually do perfectly destructive unless the two slits have unequal width. If the two slits are identical, then their individual amplitudes at any point are going to be nearly equal. বুঝে গেছে?
Yes, sir.
আচ্ছা, because it is nearly equal, so typically the subtraction result gives us 0. So that works. আর তুমি আমাকে যে কোশ্চেনটা করছিলে একটু আগে, সেটা হচ্ছে what if we do both of the changes simultaneously? Both the changes simultaneously means what if we make the top one slightly bigger and the bottom one slightly smaller? Then what's going to happen? Let's have a look. No big deal. Let's try to understand. Let me give some numbers in this case so that it will be easier for us to grasp, because other than that, whenever I'll do the subtraction, things might get really weird. So I'm going to write this whole information right now with this dark line, with purple blue. Let's say initially both of the slits had amplitudes delivered of, let's say, 5 and 5. Let's say we increased it by a factor of 2 and we decreased it by a factor of 1. This is what you asked for, right?
Yes, sir.
Okay. So what is going to happen at the possible bright fringes? So if you consider for one of the bright fringes, this is going to be 5 plus 2 plus 5 minus 1. So we're going to get how much? 11. Earlier, which used to be 5 plus 5 equals to 10. So because the total sum is bigger than earlier, in this case, the bright fringes will be brighter. Now, what happens to the dark fringes? This will come as the difference of 7 and 4. So here the total value was 7. Here the total value is currently 4. So the difference of 7 and 4 is how much? 3. When this change was not brought about, this used to be perfectly 0 because this was 5 minus 5 equals to 0. Now we have some light remaining, which means the dark fringes will also become brighter. So bottom line টা হচ্ছে এরকম, বললাম আমি জিনিসটাকে ইজিলি সামারাইজ করে দিচ্ছি. Try to understand. If we have mismatching slit widths, মানে এই দুটো slit width যদি somehow exactly equal না হয়, dark fringes will always become bright because the subtraction result will be non-zero. কথাটা আমি আবার বলতেছি. If the two slit weights are somewhat mismatching or they are not equal, the dark fringes are always going to become brighter. because the subtraction result is gonna be non-zero. However, if we increase the however, what will happen to the bright fringe is directly related to what are we doing to bring about the change. If we increase the slit width, then the bright fringes become brighter. If we decrease the slit width, then the bright fringes become darker or dimmer. বুঝা গেছে? এটা একবার বলবো।
জি স্যার।
For dark fringes, mismatching slit weights or unequal slit weights will always result in the dark fringes to become brighter compared to equal slit widths, because whenever the slit widths are equal, the subtraction result gives you perfect zero, which means there is supposed to be perfect darkness. But whenever they are somewhat mismatching, one big, one another small, or another small, the other one big, if they are not equal, whether you have increased the size of one or you have decreased the size of one, doesn't matter, as long as they are unequal to each other, the subtraction result will be non-zero. The subtraction will be non-zero, which means the dark fringes would still have some light remaining, some amplitude remaining, which means they will become brighter. So no matter what we do, whether we increase the slit width or decrease the slit width, the dark fringes will always become brighter because the subtraction is non-zero. You have some light remaining, all the lights did not get cancelled out. এটা হচ্ছে dark fringes জন্য. However, for the bright fringes, the behavior is exactly what we are doing to the slit width. If we increase the slit width, more light is passing through, so bright fringes is becoming brighter. If you are decreasing the slit width, less light is passing through, so the bright fringes are becoming dimmer, because bright fringes work with the sum of those two. So if the sum is bigger, you have brighter light. If the sum is smaller, you have dimmer light. That's it. Make sense?
Yes sir.
আচ্ছা, এইটুকু গেল হচ্ছে আমাদের double slit related stuff. I might as well pick up some MCQs just to give you a bit of an idea what type of questions we are going to go through, and then we might as well pick up the other thing, the diffraction grading. So let's see some MCQ questions. I'll make them available for you to practice, don't worry. All right, so these are the typical questions, some of those things that we have to work with. They're pretty interesting, to be honest. So let's say we'll go for this one. 8.2 question number 1. Try question number 1. Read and see if you can solve it. So কোনটা হবে correct answer?
স্যার সি কি হবে?
C is the correct response. বুঝছো কেন?
জি স্যার, আমি
Because
এ নিয়ে একটু গুলিয়ে ফেলেছিলাম, বাট সি
no, A is not gonna be the correct response. A can be said, OX can be said to be the half of the slit width. If you think from the central maxima to the first dark fringe, this much is half of x. X মানে হচ্ছে ওই যে lambda equals to x by d এর x. আচ্ছা, anyway, 2 is good. আচ্ছা, number 3 টা try করো. Number 3 can be attempted by this relationship that I just showed over here, that I wrote some proportionalities over here. এইটা I would like you to write this thing, lambda d equals to ax, somewhere in your paper, and use this equation to figure out the answer for question number 3. So which one do you think is the correct response?
B.
Okay, I'll give some more time, because answers are coming in doesn't mean that you have to stop thinking. Attempt, use your brain, rest of you. That's one response from one student, but I want you to respond, every one of you.
স্যার আমার মনে হচ্ছে আইদার সি অর এ।
Okay,
স্যার আমার মনে হয় এ হবে।
let's try to see. Our teacher sets up an apparatus shown to demonstrate two-slit interference pattern on the screen, which change to the apparatus will increase the fringe spacing. Let's copy this question up and try to equate the variables. Have some space over here. But I shouldn't have had done that. All right. All right. So the equation that we usually work is lambda equals to x by d, or lambda d equals to x. এখানে এই কোশ্চেনের জন্য p is practically not any variable of this equation. Try to understand. This thing is a. This thing is d. The fringe separation is x, bright to bright or dark to dark. P is not at all a variable that controls x. X is dependent upon these three variables. Because what is P? P is the distance from the single slit to the double slit arrangement. This was not a part of this whole setup. So this is not the correct answer. Now you think about it, which one of these three can be the correct response? Try again. I'll help.
Sir, B.
G sir, B.
Sir, B.
Okay.
B.
We want to increase the fringe spacing, right? We want to increase the fringe spacing. So in this equation, x has to go up. To make x go up, we either have to have the lambda go up, or d go up, or a go down. ঠিক না?
Yes, sir.
তোমরা কোনটা বলছো? b বলছো?
Yes,
Yes,
sir.
sir.
Decreasing the distance q. q যদি ছোট করে ফেলি তাহলে x বড় হবে. Yeah, that sounds about correct. I think B is the correct response.
Sir,
বলো.
আমাকে একটু আরেকবার বলবেন যে a ডিক্রিজ হলে x কেন ইনক্রিজ করবে?
Because these two variables are on the same side of the equation. So they are inversely proportional. When these two are constant.
Okay, আচ্ছা বুঝছি স্যার।
বুঝছো?
জি।
আচ্ছা। আচ্ছা, D নাম্বার কি বলছে একটু দেখি আমরা। Decreasing the wavelength of the light. Decreasing the wavelength মানে হচ্ছে আমরা যদি কমা ফেলে x আর কমে যাওয়ার কথা, so D হবে না। So ultimately correct answer হচ্ছে B. বুঝে গেছে সবাই এই কোশ্চেনটা প্রপারলি?
জি স্যার।
কিছু কিছু কোশ্চেন অনেক সময় তো এরকম করে যে মনে করো এরকম একটা সিমিলার একটা কোশ্চেন তোমাকে দিল, এইগুলার কোনোটাই কারেক্ট আনসার হচ্ছে না। লাস্টের কোশ্চেনে তারা বলছে ডিক্রিজিং দ্য ফ্রিকোয়েন্সি অফ দ্য লাইট। দেখো এখানে কিন্তু কারেক্ট আনসার হবে ডি। মনে করো এই তিনটা যদি আনসার না হয়, এটা কিন্তু কারেক্ট আনসার হতে পারে, বিকজ ডিক্রিজিং দ্য ফ্রিকোয়েন্সি মিন্স হোয়াট? ইনক্রিজিং দ্য ওয়েভলেন্থ, ঠিক না?
জি স্যার।
এই কোশ্চেনে কিন্তু ফ্রিকোয়েন্সি নাই, আছে? There is no mention
No,
of
sir.
frequency over here, but there is a wavelength mention over here. So sometimes MCQs can also show up in this way, that if the frequency is decreased, so lambda will increase, that will evidently affect the x to become higher. So এইটাও আমাদের একটু খেয়াল রাখতে হবে যে আমাদের কোশ্চেনে ফ্রিকোয়েন্সি রিলেটেড কিছু বলছে কিনা, সেটার ইফেক্ট কি হচ্ছে। We have to keep our eyes peeled for those kind of information. আর কিছু কোশ্চেন আমরা দেখি যারা একদমই আওয়াজ টাওয়াজ করতেছো না। একটা হচ্ছে সাদিয়া, লেকচার কি বোঝা যাচ্ছে?
জি স্যার, বোঝা যাচ্ছে।
শরীর খারাপ?
হ্যাঁ, ওরকমই।
আচ্ছা, গেট ওয়েল সুন। শৈলশ্রী? উজমা? Are you kids here?
Sir.
Shoilosri and Uzma, are you kids here?
Sachi.
Yes, sir.
Okay. Radia Sarwat. এটা কে? I can recall your face. Oh, আচ্ছা, yeah, I do recall your face. আচ্ছা, কোশ্চেন না, কিছু না বুঝলে আমাকে কোশ্চেন করো প্লিজ, ঠিক আছে? Let's not just keep
স্যার।
বলো।
স্যার, এই যে কিউ কে ডিক্রিজ করলে ফ্রিঞ্জ স্পেসিং যে ইনক্রিজ করবে, এটাকে ম্যাথমেটিক্যালি ছাড়া অন্য কোনো ওয়েতে বোঝানো যাবে?
অ্যানিমেশন ছাড়া আরেকটা জানি কি বলে এটারে, যেটা দিয়ে অপারেট করা যায়? যে
Simulator.
সিমুলেটর, হ্যাঁ এক্স্যাক্টলি। আমি এই ওয়ার্ডটা না সবসময় ভুলে যাই। Let's see if we have any. Love these people who made these things. It, okay. So this is the single wave frequency. Let's use two slits. এটা কমানো যায় না? এটা কি? এটা স্টপ ওয়াচ। এটা কি? ওয়াটার লেভেল। ওরে। আচ্ছা, এটা কি? মেজারমেন্ট ডিভাইস। আচ্ছা, দাঁড়াও দেখাচ্ছি। এই হচ্ছে আমাদের ডাবল স্লিট বিহেভিয়ার। সেন্ট্রাল ম্যাক্সিমা 1 2 8। এই যে স্লিট সেপারেশন, স্লিট সেপারেশন যদি এখানে আমি কমায় দিই, আচ্ছা এটা একটু ভালো মতন বোঝানো যাবে। মনে করো লেটস সে I don't want electric field. ওকে, স্ক্রিন পাওয়া গেছে। স্ক্রিনটা খুঁজেছিলাম এতক্ষণ। সো এই দেখো হচ্ছে এই হচ্ছে আমাদের ওয়েভগুলোর স্ক্রিন। এই যে এটা হচ্ছে আমাদের সেন্ট্রাল ম্যাক্সিমা ব্রাইটেস্ট, এটা হচ্ছে ডেস্ট্রাকটিভ, এটা হচ্ছে ডেস্ট্রাকটিভ 1, এটা হচ্ছে ম্যাক্সিমা 2, ডেস্ট্রাকটিভ 2, ইট গোজ অন। এই প্যাটার্নটা তো বুঝছো? এতক্ষণ আমরা এটা নিয়ে আলাপ করতেছিলাম।
জি স্যার।
ঠিক
জি
আছে?
স্যার।
যদি আমি স্লিট সেপারেশন যদি কমায় দিই তাহলে দেখবো হচ্ছে এটার উইডথটা বেড়ে যাবে। সেপারেশন যত কমাবো এটা আস্তে আস্তে আরো ওয়াইড হবে। এটা আসতে সময় লাগতেছে বিকজ দ্য ওয়েভ ইজ চেঞ্জিং। এই যে দেখো স্লিট সেপারেশন এখন দেখো এক্স কত বড় হয়ে গেছে। এখানে হচ্ছে সেন্ট্রাল ম্যাক্সিমা, এইখানে হচ্ছে আমাদের আমাদের ইয়া কি বলে ফার্স্ট ম্যাক্সিমা, whereas this is the first minima. So these waves are getting more spread out whenever the two sources are really close to each other. Whereas if I increase the slit separation, you will see that you will be able to see a lot of patterns over here. এই যে দেখো কতগুলো প্যাটার্ন চলে আসছে, which means the entire shape of the wave of the interference got squashed in. বুঝছো?
জি স্যার, থ্যাংক ইউ স্যার।
আচ্ছা, এটা geometrically explain করার একমাত্র উপায় হচ্ছে by construction. That's why to help for the from the simulation. Simulation actually helps for those purposes. This is a good simulation, to be honest. Wow. 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 This is really beautiful. Kids, do you know if you find it beautiful?
Yes.
Yeah.
Sir.
Oh my God. What? What? This is out of this world. Shit. This is unbelievable. প্রমাণ দেখতেছো?
Yes, sir.
Yes, sir.
This is beyond my expectation. This exists. Wow.
Yes, sir.
I'm practically speechless.
And this is really helpful for like understanding this chapter too.
Yeah, exactly. I mean, visualization always helps a lot other than basic description. I mean, simulations are, like I said, these people are God. এখানে screen দেওয়ার option নাই না? হ্যাঁ, এখানে screen দেওয়ার option because this is supposed to be the screen because this is a water wave that we're seeing from the top. All right, I think I have played enough. You can also try to do that. This is the first thing that shows up if you write double C simulator in the fedcolorado.edu simulations website. So you can go there and do stuffs if you want. Love it. Acha. How about we give it a try for number 6? এটা করার জন্য তোমাদের কাগজ কলম লাগবে, সো একটু লিখতে হবে, লিখে ক্যালকুলেটর দিয়ে ট্রাই করে এমসিকিউটা দেখো সলভ করা যায় কিনা। নাম্বার 6
Sir, X তো ছিল distance না between the fringes.
হ্যাঁ আমি বুঝি নাই
X টা distance between the ওই যে fringes এর distance যেটা ছিল মানে এর মাঝখানে যে distance গুলো ছিল ওটা X না?
না 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 আমি এক্স কোথায় দেখাচ্ছি তোমাকে, দাঁড়া 1 মিনিট। এটা দেখো, এ হচ্ছে, এটা মনে রাখার সহজ বুদ্ধি আছে। Try to remember this formula. মানে the way I usually remember this, lambda a x নিচে হচ্ছে d, so lambda equals to x by d. lambda হচ্ছে সোর্সের lambda, a হচ্ছে সেপারেশন, d হচ্ছে ডিসটেন্স বিটুইন देम, আর x টা হচ্ছে স্লিট সেপারেশন, সরি ফ্রিঞ্জ সেপারেশন। বুঝছো?
জি স্যার।
ট্রাই করে দেখো কি হয়। What does I'll copy and place it on my thing. I cannot copy this. Yes, I can. So এখানে for the first equation 700 into d equals to a into 3 তো বলছে 350 into d চেঞ্জ করে নাই, d নিয়ে কোনো কিছু বলে নাই, তার মানে d আনচেঞ্জড। স্লিট সেপারেশন ওয়াজ ডাবল, তার মানে 2a into what is the new fringe spacing, তার মানে এটা আমরা বাই করতে বলছে x is the unknown here। দুটো ইকুয়েশন ডিভাইড করে দাও, dt বাদ কাটলে হবে 2a বাদ 2 বাদ না 2 তো বাদ যাবে না, তার মানে আসছে হচ্ছে 2 equals to 3 divided by 2x। তার মানে হচ্ছে 4x equals to 3, x equals to 3 by 4, 0.75। এটা আনসার চেক করো তো কেউ 0.75 হয়েছে কিনা, তোমাদের কাছে আনসার বুকলেট আছে না?
স্যার দেখি দাঁড়ান।
এটা হওয়ার কথা। না হলে তো সর্বনাশ, আবার করা লাগবে। এটা হচ্ছে তোমার, আচ্ছা এমসিকিউ নাম্বার হচ্ছে 8.2 এর কোশ্চেন নাম্বার 6
ঠিক আছে,
হইছে?
হ্যাঁ এই হবে।
গুড। দেখো বুঝছো কিনা আমি কি করছি? I wrote the equation lambda d equals to x for the two given scenario. So lambda d equals to x was my equation. So first scenario তে আমাদের ছিল ওয়েভলেন্থ ছিল 700 নানোমিটার, d নিয়ে ওরা কিছু বলে না, ওই জন্য d টাকে আমি ভ্যারিয়েবল ফরম্যাট d তে লিখছি। and then the fringe spacing কত হবে সেটা নিয়ে কিছু বলে নাই, সো ওটাকে মানে অ্যামাউন্ট বলে নাই, ওই জন্য আমি ওটাকে ওই ফরম্যাটে লিখছি। and it they said this was 3 millimeters, I wrote only 3. The reason I did not bother about the units over here, because this wavelength was given in 700 nanometer, the next wavelength was also given in 350 nanometer, so I can see that their units are same, so I didn't have to bother about the units, because that's why I only wrote only the numbers. In the same way, the first fringe separation was given by 3.0 millimeter, and I was trying to find out the new fringe separation for the second setup in millimeter scale as well, because all of these answers were given in millimeters. That's why I did not bother to write the units. This is just a smart way, or you can say a time-saving way to do your MCQ math. But you have to be observant for that, so that you don't miss up information, important information if there is. So I wrote those two equations and then I divided them. So all the relevant stuff goes away. So এখানে একটা 2 ছিল, এখানে একটা 2 ছিল, so I wrote ultimately 2 equals to 3 by 2x, and that pretty much gives me this answer. বললাম বুঝছো কি এটা কিভাবে করছি? এভাবে করাটা আমার মতে সবচেয়ে বেশি কনভেনিয়েন্ট। However, there is another way to solve the same question. আমি অল্টারনেট একটা উপায় দেখাচ্ছি, খেয়াল করো। অল্টারনেট উপায়টা হচ্ছে এটা, মানে আমি দুটো উপায় দেখাচ্ছি, তোমাদের যার কাছে যেটা ভালো লাগে, যেটা মাথায় নিতে ইজিয়ার হয়, ওটা দিয়ে করবা। ল্যামডা ডি ইকুয়ালস টু হচ্ছে ax, তো আমি দেখতেছি হচ্ছে x is proportional to lambda, ওদিকে x is inversely proportional to a, ঠিক না? আমি d
জি
টা লিখি
স্যার।
নাই, কারণ এখানে d টা আমার ভ্যারিয়েবল হিসেবে এখানে নাই। সো আমি 700 থেকে চেঞ্জ করে 350 করছি। সো when lambda becomes lambda by 2, x should also become x by 2, তার মানে এখান থেকে একটা চেঞ্জ ফ্যাক্টর পাইলাম হাফ। Similarly, when the slit separation is doubled and x এর সাথে slit separation is inverse, so when a becomes 2a, x should become half x, because এটার সাথে inverse proportionality, so এটা যদি ডাবল হয় তাহলে slit separation কি হবে? হাফ হবে। তো দুইটা ফ্যাক্টর মিলে টোটাল চেঞ্জ কত পেলাম? এখানে পেলাম হাফ হবে, এখান থেকে পেলাম হাফ হবে, তার মানে আলটিমেটলি আমাদের এক্সট্রা হয়ে যাবে হচ্ছে 1/4 অফ অরিজিনাল এক্স। সো তুমি এখান থেকে সরাসরি 1/4টা বসায় দাও, 1/4 into 3.0, that also gives you 0.75 মিলিমিটার। এভাবেও করতে পারো বেসিক প্রপোর্শনালিটি কনসেপ্ট দিয়ে। বললাম বুঝছো কি এখানে কি হয়েছে, ঘটনাটা কি ঘটছে এখানে?
জি স্যার, বুঝেছি।
ঠিক আছে? সো
জি স্যার।
যেটা তোমাদের কাছে ইজিয়ার মনে হয় বা যেটা টাইম সেভিং মনে হয়, পরীক্ষা হলে যেটা মাথায় হঠাৎ করে আসে, if you know both of them, this is always helpful, but whatever you feel comfortable, ওটা দিয়ে ট্রাই করতে পারো। আচ্ছা, আমি এই এমসিকিউ পেপারটা তোমাদের আজকে আপ করে দিব। if you kids want, you can actually attempt the rest of the MCQ questions which would be nice. আর নেক্সট ক্লাসে আমি তোমাদেরকে ইয়া পড়াবো, ডিফ্রেকশন গ্রেটিং পড়াবো। সো ডিফ্রেকশন গ্রেটিং ইজ দ্য নিউ থিং।
স্যার নোটস গুলো দিয়ে দেন।
আচ্ছা হ্যাঁ, নোটসগুলো একটু গুছাইতে হবে। নোটসগুলো যে ফরম্যাটে আছে ওখানে সবকিছু নাই। আমি আমার পুরো নতুন মানে A2 স্টুডেন্টদের কাছ থেকে আরো কিছু রিসোর্স গ্যাদার করে পুরোটা একবারে গুছায় তারপর তোমাদের দিব। I'll definitely upload this before your next class. Don't worry about that.
আচ্ছা স্যার,
জি বলো।
স্যার মা আমাকে জিজ্ঞেস করেছিল যে মানে আমাদের মক কবে থেকে শুরু হবে, আপনি
তোমাদের
কি কিছু বলেছিলেন?
বলতেছি তোমাদের চ্যাপ্টার ওয়াইজ টপিক টেস্ট হবে হচ্ছে পুরো in the entire month of January. The whole month of January will be chapter wise topic test and full
আচ্ছা
syllabus mock will happen from February through April. 3 মাস। আমরা ডিসেম্বরের মধ্যে
ওকে
আমরা
স্যার,
সিলেবাস শেষ করব। এবং আমরা
ইনশাআল্লাহ স্যার।
এর সাথে আরো যে প্র্যাকটিস গুলো আছে ইনশাআল্লাহ হ্যাঁ we will cover those as well. Okay, আল্লাহ হাফেজ, গুড নাইট।
আসসালামু আলাইকুম স্যার।
Good night, sir.
Right, sir.